Till now we have seen how to find out strain energy or elastic strain energy for a screw dislocation and an edge dislocation. Now we'll be looking at how to find out elastic strain energy for a mixed dislocation. So for a mixed dislocation, what we do is we just do a superposition of elastic strain energy parts of edge and screw dislocation. So let's consider a mixed dislocation. How you define mixed dislocation? So let's say this is our dislocation line, and when I say mixed dislocation, what I really mean is the Burgess vector makes some angle with the dislocation line. So let's consider this is the Burgess vector B, which makes an angle phi with a dislocation line. Now when I want to find out an energy of a mixed dislocation, I do superposition of elastic strain energies of edge and screw dislocation. So let's find out the components of this B in terms of edge part and a screw part. So for edge part, you can see that this can be BE, which I am writing it here as B sin phi, and BS, which is nothing but a screw part of this mixed dislocation. I can write it as B cos phi. Now using this superposition of edge and screw parts, we can find out an elastic strain energy per unit length to be equal to GB square. So note here that the Burgess vector which we are using is an edge component of this mixed dislocation, or the Burgess vector, that is B here, and here this is an elastic strain energy for a screw dislocation, and here I am using a Burgess vector, a component of a Burgess vector having a screw characteristics. Now I can write this B in terms of B as B sin phi. So here it becomes B square sin square phi, and here in this case I am replacing BS with B cos phi. Now I get the term to be equal to B square cos square phi. And when I simplify this, what I get a relation or an equation for elastic strain energy per unit length of a mixed dislocation. So it comes out to be GB square 1 minus mu cos square phi upon 4 pi 1 minus mu ln of r upon r naught. So from this relation or equation, you can see that elastic strain energy for a mixed dislocation also is proportional to B square, that is a square of a Burgess vector. And thus you can say that this elastic strain energy per unit length of a dislocation can be minimized if the Burgess vector is small. So that's why you can say that the shortest lattice translation vectors are preferred, as because we have the shortest translation lattice vectors and we have seen that they become a Burgess vector. Why? Because if we have a slip along shortest lattice translation vectors, this elastic strain energy per unit length of a dislocation can be minimized. And this has a great implication. We have seen this, that energy of a screw dislocation or an edge dislocation also is proportional to B square. Now let's look at this example where you have a Burgess vector, and you can see that the Burgess vector magnitude is B1, and here is an edge dislocation which we have shown. So here you can see there are two extra half planes, and this scenario can be possible where you have two extra half planes in case of an abscissa or in case of an edge dislocation present in an abscissa crystals. And this B1 can be dissociated into B2 and B3 in this way here, which we have shown. So this dissociation of B1 to B2 and B3 can only be feasible with certain criteria, and let's look at those. So this splitting of a dislocation with B1, let's say here in this case this B1 is equal to, let's say let's mark the Burgess vector here. So we have a Burgess vector which will be a shortest lattice translation, so this will be B, and thus B1 I can write in terms of this B as 2B, whereas B2 and B3, these two Burgess vectors, I can write as B2 equal to B3 equal to B. And now using this relation where we said, let us write it down, we said that E is proportional to B square. So with this relation, we can say that E1, that is energy associated with this dislocation having Burgess vector B1, will be proportional to B1 square, and B1 is nothing but 2B, so it becomes E1 is proportional to 4B square, while E2 and E3 are proportional to B square, and thus even if we add E2 plus E3, it becomes 2B square. And you can say that, let us write it down, so E2 plus E3 becomes 2B square, and E1 we have figured it out to be 4B square, and thus this is smaller, and thus B1 can split into two Burgess vector B2 and B3. Now let's look at a general case of splitting of dislocation, and that is called as Frank's rule for dislocation dissociation. So let us consider a dislocation. This is a dislocation line and it is a Burgess vector B1, and we can say that this B1 can dissociate to B2 and B3, these two dislocations. And let's look at this dissociation and how is it feasible, or what are the criteria for this dislocation to dissociate into B2 and B3. We have seen energy as a criteria. Here let's look at B1, and let's consider that we can write B1 in terms of B2 and B3. Let us consider the included angle between B2 and B3 to be phi, and now based on this angle we can say that whether B1 can be dissociated into B2 or B3 or not. So let's do that. So let's consider a condition with angle phi. So when phi is greater than pi by 2 but less than or equal to pi, reaction is preferred. We'll be seeing it. And when phi is greater than 0 but less than pi by 2, then dissociation is preferred. What does that mean? When this condition is met, let us write it down and understand it. So what I'm exactly saying, when I have B2 and here it is B2 and here it is B3, and this is B1. So here, if this angle, this is phi, if this angle is less than pi by 2 with this condition, you can clearly see that B1 is much higher than B2 and B3, and thus B1 can dissociate into B2 and B3, or we can say that B1 square is higher than B2 square plus B3 square. So let's consider why pi by 2. So we have B2 here and we have B3 here, and let's consider this to be 90, or what I can say that the included angle to be 90. So in this case you can say that B1 square equal to B2 square plus B3 square. So this is from a Pythagoras theorem. So if the angle is 90 degree, this condition is satisfied. If angle is less than 90 degree, you can say that B1 square must be higher than B2 square plus B3 square. And if angle this angle is more than 90 degree, you can say that B1 square must be smaller than B2 square plus B3 square. And thus the reaction is preferred. What do I mean by that? So if the angle is greater than 90 degree and less than equal to pi, so this B2 and B3 will combine to form B1. Then that is why it is called as a dislocation reaction. So here in this case, B1 square must be less than B2 square plus B3 square. So based on this angle, included angle between B2 and B3, we can say that whether the reaction is possible between dislocations or dissociation is possible for a dislocation. Now let's understand this dislocation dissociation for FCC crystal. So we have seen, or we have discussed this, that there is a this is a shortest lattice transition vector, and for FCC it is half 110. This is what we have seen. And we also have discussed that this is a perfect dislocation, and there are dislocations which are partial dislocations. So this dislocation can split. So when we discussed about partial dislocation, we have discussed that this dislocation can split into two partials in this fashion. So I have these two partials, and this is a perfect dislocation. So let's call this perfect dislocation as B1 and these two partials as B2 and B3. So we can say that this B1 can dissociate into B2 and B3. So whether that is feasible or not, let's find it out. So this B1 is A by 2 1 bar 1 0, and this B2 and B3, these two partials, are A by 6 1 bar 2 bar 1 plus A by 6 2 bar 1 bar 1. So these are the two partials. And what do I mean by partial? Because when this dislocation is, or like this dislocation is from starting from one lattice point and ending at another lattice point, so I call this as a perfect dislocation. But here I am calling it as a partial because there is no lattice point here present. So that's why these dislocations are called partial dislocations. Now let's find out from this criteria, energy criteria, you can find it out that whether B1 square, so let's do that, B1 square will be A square upon 2, B2 square will be A square upon 6, and here also B3 square will be A square upon 6. And you can see that the B1 square is greater than B2 square plus B3 square, and thus we can say that this dislocation can dissociate into B2 and B3. So B1 can dissociate into B2 and B3, and this is feasible. So thus in FCC crystals, the perfect dislocation, that is B1, which is nothing but A by 2 1 bar 1 0, can dissociate into two partials B2 and B3, and having indices as A by 6 1 bar 2 bar 1. So we can see that B1 can dissociate into B2 and B3, and we can find it out using this energy criteria, where energy is proportional to B square, that is Burgess vector square. Now let's get introduced to an important terminology for dislocation, that is line tension of a dislocation. So we have seen, let me write it down, we have seen energy per unit length. So this was energy per unit length of a dislocation line. We have figured it out to be alpha GB square, and thus we can say that as I increase the length of this dislocation, the energy of the dislocation will increase. Thus dislocation will try to reduce down its length or minimize its length. So let's understand what is line tension of a dislocation. So you must be knowing about a surface tension, and this line tension is analogous to surface tension. So surface tension has a unit of energy per area, and whereas line tension of a dislocation is written as energy per unit length. So we have found out what is a line tension or elastic strain energy per unit length. So we can consider that line tension is equivalent to elastic energy per unit length, and thus we can write that line tension is equal to alpha GB square. So as I mentioned you, the strain energy of a dislocation is proportional to the length of a dislocation. So let us understand this. Let me write it down. So we have a dislocation here. So this dislocation will try to straighten as much as it can because it reduces down its length. So let's say if I consider this as ds1, and let's say I consider another configuration of this dislocation as ds2. So this dislocation 2 will have more energy. So we can write it that for 2 it has more energy as compared to dislocation 1. So thus this dislocation will try to minimize its length, and the force which or the tension which tries to reduce its length is considered as a line tension of a dislocation. And let's look at this line tension in more detail and why this dislocation will become curved or increase its length, because we have forces acting on a dislocation. Let us write that. So when we subject a crystal to deformation, there will be forces, and these forces acts perpendicular to this dislocation line, and we have seen this forces makes this dislocation curve in a curved way. If there are no forces acting on a dislocation, the dislocation will try to become as straight as it can, so that it can reduce down its energy or strain energy of a dislocation. So consider a dislocation line. Let's consider this dislocation line A and which is pinned at A and B, and under the application of force, let us write it here. So under the application of force, we can say that this dislocation gets curved. This dislocation line will get curved. So it gets curved in this fashion, and so let's consider a tau to be of shear stress which is acting on dislocation and which is maintaining its curved nature. So let's consider the length of this dislocation to be ds, and the radius for this curve, let it be r, and let us consider this angle to be d theta. So this tau makes this dislocation, straight dislocation, in a curved way. And so what is this tau which can retain this curved nature of a dislocation? So we have to find out a tau which makes this configuration of dislocation stable. So when we see the geometry of this dislocation, as this we are considering a very small length of a dislocation, so this d theta is much small, and thus we can consider that when you draw a tangent here, it makes an, so this angle will be d theta by 2, and this angle also will be d theta by 2. Let us mark that also. So these angles are d theta by 2. Let us consider a force per unit length of a dislocation which we have defined when we apply a shear stress tau, and let's consider this for F to be a force per unit length of a dislocation. And let us consider the line tension of this dislocation to be T, which makes this curved dislocation, or which tries to make this curved dislocation a straight line so that it minimizes its elastic strain energy. So let's consider this T to be a line tension of a dislocation. So now if you do a force balance, we can say that the force per unit length of a dislocation, we have defined it as F, and the ds is the length of a dislocation. So we can find out a force, a combined force acting on a dislocation. Let's consider that it acts, let us write it down. So it acts here. So this will be F ds, and it must be equal to, or it must be balanced by a downward force. So we can say that let us write that down also. So we have T here, and the downward force will be T sine d theta by 2, and we have this two tensions here. So here it will be 2t sine theta by, so that is what the term here is representing. So we have 2t sine d theta by 2, and we said that this d theta is much small, so we can write that sine d theta by 2 as d theta by 2. Now since this ds we can write using this geometry as r d theta, and F, that is force per unit length of a dislocation line, in terms of a shear stress which we have applied, we can write it as tau b, where b is a Burgess vector. And when we replace this in this relation, what we get is that tau br d theta equal to alpha gb square. So T we are replacing here as alpha GP square into d theta. And when we rearrange, what we get that the shear stress equal to alpha GP upon R. So we had this straight dislocation and which was made into a curved dislocation when we apply a shear stress tau, and this shear stress tau is given as alpha GB upon R, where R is the radius for this curvature. So this equation has an application in dislocation theories, and we'll be seeing it. So we'll be using this relation frequently as we move along in our course. So here you can say that this is shear stress tau, which is required to maintain this geometry of this curved dislocation. So this makes this curved dislocation stable when we apply this much stress. If we don't apply this stress, so this curved dislocation will tend to go or tend to become a straight dislocation. So P will see the bowing of dislocations or bulging of dislocations, and will be using these relations frequently to find out a shear stress to maintain this geometry of the dislocation. So with this, I will stop here.